We will now discuss the fundamental theory derived in our undergraduate mechanics course, which is called Engineer's Beam Theory, or in other words, Flexure Beam Theory. Theory of elasticity, which is the main focus of advanced structure mechanics, is an advanced version of engineer's beam theory. Before starting theory of elasticity, I think so it's a good idea just to recall the engineer's beam theory and discuss drawbacks of this theory. Based on those drawbacks, we will develop a new theory which is called theory of elasticity. Before starting any theory, it is important to appreciate the assumptions based on which the whole theory has been formulated. The assumptions of engineer's beam theory are as follows. Plane section remain plane, material is homogeneous and obeys Hooke's law, modulus of elasticity for compression and tension are equal, beam has got constant cross section and is straight initially before application of the load. And finally, the plane of loading must contain a principal axis of beam cross section, and loads must be perpendicular to the longitudinal axis of the beam. In all these, the most basic assumption is assumption number one, which is plane section remain plane. This is the backbone of reinforced concrete theory of beams and steel design of beams. This assumption says that a beam cross section, which is a plane, will remain straight after bending. We will see that using this assumption, the calculations become very simple and we get a very simplified form of flexure formula. Later, we will relax this assumption and we will develop a more generic form of theory, which will be called theory of elasticity, which won't be limited to only plane section remaining plane after application of the load. The engineer's beam theory is good for ordinary beams which have got cross section very small as compared to the length. If we have structures such as deep beams or walls, then engineer's beam theory gives us wrong answers. It is those structures for which we will be developing the theory of elasticity. The second assumption, which is material in beam is homogeneous and obeys Hooke's law, has been touched upon previously. We discussed that the stress equation is derived for a body which is homogeneous. Homogeneous meaning that body is continuous and cohesive. Continuity of a body means that there are no cracks or gaps in the body. The body has got a uniform surface. Cohesiveness, on the other hand, means that the molecules making up the whole body are uniformly distributed around the body. The molecular structure has got no gaps or no voids. The whole structure is a solid mass. Stress is equal to E times strain is another assumption of engineer's beam theory, and we have already discussed how stress is equal to E times strain is important for different bodies. The third assumption is that moduli of elasticity for tension and compression are equal. So, like steel, we have the modulus of elasticity both in tension and compression the same. Assumption 3 can be adjusted to, to meet those materials which don't have modulus of elasticity in tension and compression equal, such as reinforced concrete. In reinforced concrete, we have got a compression section, which is normally concrete, and a tension section, which is steel. And both concrete and steel have different modulus of elasticities. So we tailor the engineer's beam theory and make it suit to the RC beams. Assumption number 4, beam is initially straight and having constant cross section. Now again, assumption 4 can be adjusted for those beams which have got initial deformation and those beams whose cross section area is variable. In other words, engineer's beam theory can be adjusted to get around assumption 4. Assumption 5 says that the load applied should be perpendicular to the longitudinal axis of the beam. Longitudinal axis is that axis which is along the span of the beam. Also, the load should be applied at the centroid of the beam so that there isn't any twisting. Assumption 5 will be further discussed and elaborated shortly. As I said, assumption 2, 3, and 4, they can be adjusted if they are not getting satisfied. Assumption 1 is that assumption based on which the whole theory lies, and we can't relax assumption 1 in the case of engineer's beam theory. And we will see now in the derivation part that how assumption 1 make the calculations very easier. Let us now move on to derivation of Flexure formula. A simply supported beam which is subjected to some loading. Let us consider two adjacent sections AB and CD which are at very small distance x3 apart. We assume that the x3 is along the length of the beam and x1 and x2 are along the plane of the beam. After application of the load, the beam will bend. Imagine we take a portion of a beam. This portion clearly shows that AB and CD have moved. The BD has moved apart, where AC has moved closer after application of the load. Based on our assumption 1, AB and CD stays straight. They don't become curvy or they don't become jagged after application of the load. This assumption will only be valid if the cross-section area is very small as compared to the overall span of the beam. If we keep on increasing our cross-section area, then there is a possibility that our cross-section might become jagged. If we assume that AB and CD are extended to meet at point O, and then keeping O at center, we can draw a circle having a radius rho. Thus, EF can be a sector of a circle. EF is very close to each other. In other words, EF is very small to be considered as an arc of a circle. In general, the neutral axis is a parabolic curve. There is a difference between centroidal axis and neutral axis. Centroidal axis is a line which is passing through a point about which the whole weight is considered to be concentrated. On the other hand, neutral axis is a line about which total force is considered zero in any body. So if AC come closer to each other and BD goes further apart, then that means there is a region which is under compression and there is a region which is under tension. Then there must be a point where the section changes from compression to tension. And at that point, the force would be zero. Neutral axis is actually that line about which total force is zero. Imagine we are interested in finding out the extension of a fiber which is located at a distance x2 from the neutral axis. So we draw a line C prime D prime which is parallel to AB, and then we consider that OD is a transversal between two parallel lines AB and C prime D prime. That makes the angle subtended between OE and OF d theta equal to the angle between F d prime and D. We assume that the GH fiber is extended by HK. So in order to find out the extension of HK, we have to do some mechanics. As we discussed, that strain is change in length by original length. So for GH fiber, the change in length is x2 d theta, remembering that S is equal to r theta. That is the deformation. The original length, which is EF, that is rho d theta. Remember that EF is the fiber where no force is applied. or that is a neutral axis. So therefore, EF and GH are equal. Thus, plugging value in the strain equation, we will get the strain in the fiber GH. After this, we can multiply the strain with modulus of elasticity and get stress in GH fiber. Using this stress value, we can find stress at any fiber located within the cross section of the beam. In this lecture, we will be considering only those bodies which are at rest. We are not considering any dynamic effects on bodies. So we assume that the current body is also at rest. Under this consideration, we have to say that there are six equilibrium equations which must be satisfied. And those six equations are summation of forces in all the directions and summation of moments in all the direction must sum up to zero. Imagine that we take a small portion of this beam. This is an element of the beam having an exploratory surface. This element is in the form of a cube, i.e., it has got six sides. Please notice that we have got a neutral axis, we have got a neutral surface, which is the surface containing neutral axis, and that is in x1, x3 plane. We have got the loading plane, which is the longitudinal plane x2, x3. This loading plane is perpendicular to the neutral surface. Since we are dealing with the mechanics problem, so we have to work out the internal effects. As we discussed previously, the internal effects are either forces or moments. In this cube, we will have forces on the surface of the cube. Distinctively, we have got three different types of forces. One is the force which is parallel to x3 axis, and two are the forces which are lying in plane axis, in the plane area axis and x1, x2. So we have got one stress which is out of plane and we have got two stresses which are in plane. Since this cube has got six faces, so at every face we will have three stresses that will give us 18 stresses altogether. Later we will see that these 18 can be broken down, can be brought to 9 distinct stress components. Imagine our our exploratory surface is the one which has got the outward drawn normal in x3 direction. One thing we must have realized that in order to define a stress, we would need what phase we are talking about and what direction of force we are talking about. These two parameters will determine the stress component. So if we are talking about our exploratory area, which has got outward drawn normal in x3 direction, this would have axial stress 3 facing in x3. The first subscript of the stress means the outward drawn normal of the surface on which this stress occurs. And the second subscript means the direction of the force which is responsible to create that stress. So now stress 3-1 would mean that we are talking about exploratory surface 3 having outward drawn normal in x3 direction, and the stress is resulting from a force which is in the direction of x1. Similarly, stress 3-2 would mean the same exploratory surface with a force applied in direction x2. Please note that on every surface we have got two shear stresses and one axial stress. We divide the whole area into very small areas of dimension dA. So this whole exploratory section is made up of infinite small differential elements of dimension dA. Let us assume that we consider one small area element which is located at a distance x2 from the from the neutral axis, and x1 from the x2 axis or the longitudinal plane. At this element, we have axial stress, which is stress 33 times dA, and we have got two shear stresses, which is shear forces, which are stress 31 dA and sigma 32 dA. Now, let us apply the equilibrium equations. We start with the first equation, which is summation of all the forces in F3 direction must be equal to 0. This equation is saying that the externally applied forces must equal to internally applied force. The externally applied forces are 0. There is no external load applied in x3 direction. So we get 0 on the right hand side. On the left hand side, which is the internal effect, that we can write as sigma 33 times dA and put an integral sign having area as the variable. So that means that our small area dA time sigma 33, which is a force on differential element dA, those have to be summed up for the whole cross section in order to get the average force in the direction of x3. Sigma 33 has been derived as ex2 by rho. So plug and jug and we get ex2 by rho dA. Now E and rho, E being the modulus of elasticity and rho being the radius, they are constant for any cross section. Please note that any parameter which is not changing with area can be brought out of this integral sign. Modulus of elasticity being the property of the material is not changing with the cross-sectional area, so that can be brought out. Rho, which is the radius at which the neutral axis bends, that is constant for a particular cross-section. Rho does change as we move longitudinally, but rho doesn't change when we are moving along the cross-section area. So therefore, these both are brought out. Now we are left with x2 dA inside the integral. dA will stay inside the integral because it is an area dependent integral. x2 is the dimension along the cross section. So again, it contributes to the area. That's why it can't be brought out. If we look closely into this equation, x2 times dA is the moment of the differential area about the neutral axis. Now, this whole equation has to equate to 0. We can't have E by rho equal to 0. So, undoubtedly, x2 dA integral is equal to 0. And that is actually the first moment of area. This can be written as AX2 bar. Please note, x2 dA is the total moment of area. This is also called first moment of area. Only x2 bar in this relation can be 0. We conclude that the distance from the neutral axis to the centroid of the cross-sectional area must be 0. In other words, neutral axis must contain the centroidal axis of the cross-section. So this equation, which is x2 dA integral, that is actually the definition of a centroidal axis. And based on that, we conclude that neutral axis contains the centroidal axis of the cross-sectional area. Now let us consider the second force equation, which is summation of F2 is equal to some applied load. F2 are all the forces which are in x2 direction, and we have already discussed in the assumption that loads are applied only in the loading plane, which is this x2 x3 plane. So if the load is applied in this plane, then we have the again the external force equal to the internal force. But at this time, we would have the right hand side not equal to 0, but equal to overall applied load in the x2 direction. And that's why summation of F2 is equal to either P or V, whether we call it shear or we call it the applied load. Please note, sigma 32 is in the x2 direction, and sigma 32 times dA integral must be equal to the applied load, and that is the definition of shear. The third equation is that all the forces in the x1 direction must be equal to 0. This equation is also equal to 0 at the right hand side because we have no load applied in the x1 direction. Please note, if we are dealing with a very long steel beam which is susceptible to lateral torsional buckling, then we restrain that beam in the x1 direction. In that case, we would have some value coming at right hand side. Sigma 31 times dA summation that follows the same logic as the other forces. Let us get summation of moment about x3. Since we have no torsion applied, or in other words, no externally applied torsion on the structure, we will again get 0. However, the left hand side is showing us the the internal moment developed. The internal moment about x3 can be contributed by the shear forces on the exploratory surface. So we take stress 3-1 into dA, which is the force, time the lever arm, which is x2, and subtract that from sigma 32 dA, the force, times x1. This is this is because sigma 31 dA is causing clockwise moment, whereas sigma 32 dA is causing counterclockwise moment. Let us explore a bit further summation of M3 equal to 0. Imagine we have got a cantilever beam which is subject to a concentrated load applied at the end of cantilever. The bending moment diagram on the tension side is shown in green. Imagine that the beam is made up of I section. Please notice that we have got again typical elements in the top flange and the bottom flange of the beam. Since this is a cantilever structure, so this top flange is in tension and the bottom flange is in compression. These elements have to be equilibrated. In other words, we have to find out the forces on the faces of this cube. So this is similar to what we have done over here. In this rectangular element, we have an exploratory surface, and that exploratory surface has got these forces. We have 6 faces of the cube and 3 forces per face. So let us examine the forces getting developed on the faces of this element. We take 2 sections which are very close to one another, and these sections are 1-1 and 2-2. We can say that the moment at 2 is bigger than moment at 1. The reason is that there is a change in the moment as we go from the point of application of the load to the root of the cantilever. The moments can be divided or can be decomposed into a force couple system, which is C2T2 and C1T1. C stands for compression and T stands for tension. So as you can see, C2 and T2, they are the forces which are equal and opposite, and they are at a distance d from each other, which is the lever arm. C2 times d will give us moment m2. The same can be applied at section 1. So at section 1, we have T1, which is on the face of this cube. And at the lower flange, we have compression C1 on the longitudinal face of the cube. The reason we are calling these faces as longitudinal because their outward drawn normal are in the direction of x3, which is along the length of the beam. As we said that every beam or every element must be equilibrated or it must be balanced out. So if we have T2 applied in this direction and T1 applied in that direction, so based on equilibrium, we would need another force Fs, which is applied opposite to T2. Please remember that T2 is bigger than T1. So therefore, the Fs force has to be applied in order to balance out the force in the longitudinal direction. So if we apply a force Fs, which is in this direction, there has to be another force which is applied in the opposite direction. These two forces cause clockwise rotation. So in order to counteract this clockwise rotation, we have to apply another force which is opposite to this moment. In this way, the whole element is equilibrated. The same philosophy can be applied at the lower flange. We have compression C2 bigger than compression C1. So we will have to apply force Fs, which is cancelling the effect of F2. So the force Fs will be in the direction opposite to C2. This force will have then the opposite force on the adjacent face. These two forces which are equal, they are causing a counterclockwise rotation. This counterclockwise rotation will be balanced by by a clockwise rotation. Therefore, we have H2 direction facing towards the flange. Correspondingly, there will be another horizontal force which will be facing towards the web. H2 is facing towards the web and this force is facing towards the web. These forces will meet at the junction of the web and the flange, and then they will start flowing through the web. At the top, we have shown that the forces are moving away from the web. So, as you can see, the forces will change the direction and move apart. From this whole force system, or this internal flow of the force is called shear flow. So the shear flow starts from the edge of the flange and move toward the edge of the top flange. Please note that the applied load is resisted by the internal shear. The shear which exists at the flange is very small in proportion to the web. So it is the web shear which resists the applied external load. That is why in steel structures, we normally design the web for full externally applied concentrated load. Now, if we have X3 along the length of the beam, we can take summation of moment about x3 and we have to ensure that summation of moment about x3 is equal to 0. So H2 and H1, these both horizontal forces will induce internal moment about x3. Please note x3 is the force, x3 is the axis which is along the length of the beam. So H2 times D will be this moment, but there is another moment which is because of, say, H2 bar and H1 bar, that is along the left portion of the beam. So H2 times D must be equal to H2 bar times D in order to satisfy this condition, because we have got no external moment applied, so M3 must be equal to 0. However, what will happen if we consider a channel section. In the case of channel section, we omit this portion of the cross section. We have got only one portion of the cross section. So the forces are shown in this one portion of the cross section. Again, the H times D will cause a moment about x3. This moment has to be counteracted. Please note, if we have externally applied load P placed in the plane x2, x3, then the channel section will twist about x3. So we have to offset the load P from x3, x2 axis. This plane of loading is shown in red. This is offset at some distance from x2, x3 plane, but it stays parallel to the x2, x3 plane. Please note that in the case of I section, we had a symmetry about both axes. Because of this symmetry, our moments about M3 were internally getting cancelled out. So we didn't need to offset our loading axis. The loading axis is x2, x3. However, in the case of channel section, which is symmetrical only about one axis, we get an internal moment which is not cancelled internally. So externally, we are forced to apply the load in the axis which is offset from the loading plane x2, x3. This brings us to the definition of shear center, which is the point in the cross section of a beam through which the plane of the transverse bending loads must pass so that the beam will bend without twisting. This distance from the axis x2, x3 is called shear center. In other words, we apply the load at some shear center from the x2, x3 plane in order to cancel out the internally developed moment. So this idea is related to our summation of M3 equal to 0. Let us now consider summation of all moment about M2 must be equal to 0. So again, we don't have any externally applied moment at M2 or about x2. So therefore, we will get 0. On the other hand, the force which is responsible to cause internal moment about x2 is sigma 33 dA times x1. So we write sigma 3 dA times x1. Again, sigma 3 is EA E x2 by rho. So plugging the values and we get E by rho again out, and this time inside the integral we have x2 times x3 into dA equal to 0. This integral x2 x3 dA is the product of inertia, which is 0 only if x2 or x3 is an axis of symmetry or a principal axis. Let us elaborate on the product of inertia. Product of inertia is x2 times x3 dA integral must be equal to 0. The same argument applies that E by rho can't be equal to 0. So the product of inertia must be equal to 0. Now let us see how this works. Imagine we take an element at a distance minus x2 minus x1 from here, and another element in this quadrant at a distance plus x2 and plus x1. Similarly, we take an element in the quadrant 3 and quadrant 4 in such a way that the absolute value of x1 and x2 stay the same. If we add the product of area times these two lever arms for all the four elements, we will get 0. So an element which is at a distance x2, x1 from the coordinate axes in all the four quadrants is summed up by keeping the absolute distances x1, x2 the same. So we take x1, x2 positive for this one and this one, and we have x1, x2 negative for this quadrant and this one. These all are summing up to zero. This tells us that the axes about which we have taken these lever arms, they are principal axes. In case of rectangular area are neutral axis and the principal axis coincides. However, there can be cross sections whose principal axis and neutral axis don't coincide. Let us check them out. Imagine we have got a Z section. Again, we assume a cantilever beam which is subjected to load P. Now, this Z section has got a centroid in x1, x2 as shown. The load will be the load is applied in x2, x3 plane. However, we need to check whether the product of inertia is 0 for x1, x2 plane. So if we take a small element over here in this quadrant, do we have another small element in the opposite quadrant which can cancel out? The answer is no. In the case of rectangular section, we had an element which we could take regardless of any quadrant. Just by keeping the absolute value of the lever arm same, we could make the summation of the integral equal to 0 because cross section was symmetrical in the both axes. In the case of z-axis, or sorry, in the case of z cross section, it's unsymmetrical about both the axes. We are now in a better position to discuss unsymmetrical bending. Unsymmetrical bending is defined as the bending caused by loads that are inclined to the principal planes of bending. The example of unsymmetrical bending is, as we discussed, the roof purlins that because of inclination of roof are subjected to loads whose planes make large angles with the principal axis of inertia section. So in this figure, we have the non-symmetrical Z section and the principal axes are 1, 1 and 2, 2. The load applied is at some angle to the principal axes. Thus, this is a perfect case of unsymmetrical bending. Please note, the Z purlin are placed on an inclined roof in such a way that the resultant force lies in principal axis so that the unsymmetrical bending is neutralized. Finally, we discuss the summation of moment about x1. The moment about x1, which is the neutral axis, is equal to applied external moment. And hence, this gives us the flexure formula. So, the internal force resisting the external moment is sigma 33 times dA into x2. This will give us the moment equal to sigma 3 into x2 dA bracket. Plugging the values of sigma 3 will give us x2 square dA inside the integral bracket and E by rho kicked out of the integral bracket. x2 square dA is actually moment of inertia. So this is the area of moment multiplied with the square of lever arm or second area of moment. This is also called moment of inertia. Please note, if in our cross section the x2 is made bigger, then moment capacity of the cross section can be increased. So in the case of I cross section, the flanges are placed at some distance from the neutral axis, and that makes the cross section capacity higher. So if we are interested in a higher cross section capacity, we take that I section whose distance between the flanges is higher. Cross sections such as plate girders gives us very high moment capacity. In contrast, if we bring both these flanges together, we will have a cruciform cross section, and this cross section is very inefficient because the lever arm X2 bar is very small for the flanges. From all this discussion, it is clear that the flanges are responsible to take our moment, or in other words, to give us the moment capacity. And the web is responsible to take our shear. In the next lecture, we will try to develop theory of elasticity. We will try to get some functions for strains, after that some functions for stresses, and then use Hooke's law to combine the strain functions with stress functions.